Welcome to the Infrared Training Center's webinar on sUAS Small Unmanned Aerial System Thermography Applications. Hello, my name is Bill Schwahn with the Infrared Training Center, and I will be your host today. I've been an instructor with the Infrared Training Center for 15 years and have 20 years of thermography experience. I'm currently the sUAS Thermography Lead Instructor for course development, which includes Level 1, Level 2, and Level 1 sUAS Public Safety. My thermography background is primarily in overhead power, substations, indoor electrical, mechanical, biology, building science, and building forensics. Our first application today will be sUAS thermal imaging for flat roof and commercial buildings. Let's take a look at some objectives for this application. What a roof survey should consist of, some science and environmental requirements, how different roof materials will look differently in infrared, and some ASTM thermography roof standards. First, we have to determine what is an infrared roof scan. An infrared roof scan is a systematic thermal inspection of a roofing system with a specific intent to locate any thermal anomalies, determine the reason for the thermal anomalies, and evaluate if they may require further evaluation or remedy. It's important to note that these thermal anomalies may or may not be moisture related. A baseline survey is an initial infrared survey to determine the conditions of the roofing components. It measures key features or infrared thermal anomalies against possible future conditions. This is a great comparison for all applications because it allows the client to budget and plan for future maintenance. Infrared thermal imaging on roof membranes is not just for locating moisture intrusion under the membrane. With some roofing materials, side laps, end laps, and nailing patterns can be seen using thermography. Using an infrared camera on an sUAS for roof membrane evaluation has many benefits. It's faster than other methods of evaluation, has more options for evaluation such as producing an orthomosaic of the entire roof, and in most cases is much safer. How do you find wet insulation below the surface of a roof? First, the water must be trapped under the membrane. And the surface itself is dry. A sunny day will warm the entire roof, including any trapped water under the membrane. Early in the evening, if the sky is clear, the roof will begin to cool down by giving up its radiation to the clear, cold sky. Because of its higher thermal capacity, the wet insulation will stay warmer longer than the dry insulation and will be visible to the infrared camera. This graphic is meant to identify that the water under the membrane must be warmer than the membrane. During the day, the water, due to its high thermal capacitance, absorbs solar load, and when the solar load is off the roof, the absorbed energy in the water is given up to the clear, cloudless sky. There are times where there is thermal crossover, and the membrane and the water under the membrane are the same temperature. This would not be a good time to do an infrared thermal survey. ASTM C1153 provides roofing material thermography standards, including environmental conditions, minimum infrared camera specifications. However, the standard does not address things like different roofing materials, ballasted roofs, or roof coatings. One of the limitations of sUAS thermography is angle. The angle of image acquisition impacts the ability to identify thermal anomalies on a roof surface. The angle of image acquisition should not be less than 60 degrees relative to the target. The arrows in the image below show areas of reflection due to the improper angle of image acquisition. There are many different reasons why a roofing material might look different and infrared. One of them would be roof coatings. Roof coatings generally have a higher reflectivity and then look cooler in the iron ball. Also, different roofing materials, repairs, dirt on the membrane, debris on the membrane may look warmer as they have a higher emissivity. If you're not familiar with emissivity, check out the Infrared Training Center's Level 1 Thermography course to give you more information. This infrared roof scan was flown with a 640 by 512 sensor with a 45 degree by 37 degree field of view. It's important to understand that the combination of the sensor and lens will determine what you see on the roof deck from a given elevation off the roof deck. Using different angles, color palettes can assist us in analyzing the roofing material in flight. Also, using FLIR Thermal Studio can provide more analytical tools for your video. Understanding the composition of the roofing material and the emissivity and solar reflectivity of the membrane is essential to obtaining success when performing an sUAS survey. TPO, thermoplastic polyolefin, has a higher emissivity and higher reflectivity, while EPDM, a synthetic rubber, is black and higher emissivity with a lower reflectivity. Make sure you evaluate prior to your mission the composition of your roofing material. ASTM-C 1153 gives us some guidelines and standards. It is possible to perform roof thermography when cloudy. A 10 degrees Celsius or 18 degrees Fahrenheit temperature difference must be obtained. The roof membrane must be stable for 24 hours and must be dry. Winds less than 15 miles per hour are recommended. Our next application will be sUAS solar panel surveys. Our objectives for this application are conditions necessary for obtaining useful data, understanding the type of solar panel installed, understanding the effective angle on the solar panel, and how to obtain actionable data. The International Electrical Commission, IEC, 62446 provides industry standard requirements for thermal imaging inspection of solar panels from a UAV. Following is some of the content of IEC 62446 that we will discuss. The type of inspection, equipment requirements, inspection procedures, environmental conditions, imaging procedures. IEC 62446 identifies two basic types of inspections. One, a simplified, which is a functional check, qualitative in nature. This is defined as a limited inspection to test the basic functioning of the PV modules. And a detailed inspection. This is more detailed inspection by identifying thermal patterns and may include temperature measurements. The type of infrared sensor and lens makes a difference in the quality of the data that's collected. The minimum infrared equipment requirement per the standard are type of camera, 2 to 5, which is mid-wave, 3 to 5 wavelength, which is long wave, greater than a 320 by 240 resolution with a separate RGB camera, temperature sensitivity, or the gain, negative 20 degrees Celsius to plus 120 degrees Celsius. Geometric resolution, 3 centimeter length of edge pixel, 5 by 5 pixels inside a 6-inch PV cell. This defines the height above the solar panel that you can be to capture data accurately. As an example, 640 by 512 camera with a 13 millimeter lens, 74 feet above the panel is the highest you can fly, while a 640 by 512 camera with a 19 millimeter lens you can fly 110 feet above the panel. Sensitivity, less than 0.1 Kelvin at 30 degrees Celsius, and accuracy, plus or minus 2 degrees Kelvin. Section 4, Table 2 of the standard discusses operating current and ambient condition recommendations. Minimum operating current should be 30% of the rated current, while the minimum irradiance, that's the irradiance on the panel on the day of the inspection, should be 600 watts per meter squared. Should be noted that this should be determined by the use of a pyranometer to measure direct solar radiation, not a lux meter. Cloud coverage should be 2 to 8 sky coverage. Cumulus clouds no more than 20% cloud cover. Maximum wind speed, 17.4 miles per hour. Soiling should be none or very low. Some of the conditions necessary for success in sUAS solar panel evaluation is the optimum angle is 90 degrees, but can be as low as 60 degrees. This angle is relative to the panel, not to the horizon or the ground. Early afternoon provides the best angle of solar load and provides sufficient solar loading. Consult with the solar manager to determine the angle of the panel on the day of the inspection, or if the panel is articulating. It's important to note that IEC 62446 requires a visual image with every infrared image. This will assist in evaluation of the location of the thermal anomaly. Using thermography, you can locate damaged panels. Visually, we cannot see all the damage on this panel. However, with thermography, we can locate the damage and assess the panel. This infrared image shows that there are several strings offline. The thermal pattern may indicate typical faults such as defective cells, broken bypass diodes, delaminations and cracks, moisture intrusion, bird droppings, and shadowing. Following is a checklist for your consideration. We strongly urge you to develop your own standard operating procedures for sUAS thermal solar inspections. Number 1, know the type of solar panel you're going to inspect. Number 2, does the client just want you to take the images and submit them to them, or are they expecting a more detailed evaluation? Number 3, what are the insurance requirements? Interview the manager of the project. What angle is the panel mounted? Are the panels articulating at different angles at different times of the day? Are any of the panels offline or under maintenance? What is the objective of the inspection? Simplified or detailed? And is written permission required to fly the mission? Are just a few items that you might discuss with the manager of the project in setting up your standard operating procedures. Our next application is sUAS electrical overhead thermography surveys. These surveys provide access to components that are not accessible from the ground, providing a more detailed inspection. Following are some conditions for success. Meet with the utility to determine the following. Obtain permission to fly the utility's assets. Discuss the scope of sUAS thermography services. The utility may define the scope of service, whether it be a qualitative or quantitative thermography application. History of the components, age of the components, known challenges, and load at the time of the mission. Discuss any safety concerns to include area of flight, obstructions, distance from energized equipment for safety. The minimum on the system is very important. Insurance requirements. The utilities may require higher insurance indemnification than other applications. Load on the system on the day of the evaluation. If the system is less than 40% loaded, you will not see all the thermal anomalies that may be generated by resistive connections. This may result in thermal equilibrium, where the resistive connection is the same temperature as ambient temperature. Another condition for success is safety. What is the maximum altitude of your mission away from energized components? What is the minimal horizontal distance away from energized equipment for your mission? The utility may define this. General recommendations are 30 meters or more so that you have time to react in case of equipment failure or unknown environmental conditions. FLIR sUAS cameras have MSX, multispectral dynamics, which provides an outline around objects in the field of view, allowing for better identification of components. The following slides will provide an example of different types of imagery. This image shows a disconnect in a substation. The thermal anomaly identifies that there may be a challenge at this particular switch. This is an image of pole-mounted transformers. Note, there is a thermal anomaly at the transformer on the right side of the pole. The utility will have the background knowledge and experience to determine if this is a challenge or not. Aerial thermography can definitely show you areas that may not be visible with a handheld camera from the ground, giving you better detail. Keep in mind that just because it's a thermal anomaly doesn't mean there's a particular challenge. Always consult with the utility. In this image, we have a bolted connection with probable damage to the stranded aluminum conductor, causing barber pulling or a thermal gradient. Our next application is sUAS building surveys. This application is very broad and will identify a few of the infrared surveys that you can conduct. Following are some conditions for success for sUAS thermography. Know and understand the effects of solar load. Understand thermal capacitance and volumetric heat capacity. Wind speed should be less than 15 miles per hour or 13.03 knots. The emissivity of components will vary drastically. The image below is the side of a residential structure. This image was taken with a 640 by 512 sensor with a 13 millimeter lens. The rectangles in this image show areas of insulation defects. It's interesting to point out that the studs are also visible. This is only possible with a sufficient delta T, or difference in temperature, between the indoor temperatures and the exterior temperatures. This image of a roof identifies insulation defects in the oval and moisture intrusion under the shingles in the valley at the rectangle. This image shows another application for commercial property inspections. Air leakage was noted in the rectangle where the rooftop HVAC unit is not properly sealed to the curb of the roof. Another sUAS building science application is CMU inspection, or concrete masonry units. The concrete masonry units must have grout installed at the rebar as designed by a structural engineer. Mortar or grout in the cells will have a different or higher thermal capacitance than other cells without the mortar. Therefore, they will absorb more solar load. The inspection can be performed as soon as the solar load is off the wall. We'll take a look at some imagery in the next slide. This is an image of a concrete block wall or concrete masonry unit. Arrows show the areas of vertical and horizontal grout in the wall. Improper installation of the grout may cause structural defects. Another application may be windows. Windows will conduct energy through the glass when the argon, which is used for insulation between the planes, is depleted. When the temperature is warmer on the opposite side of the glass, the thermal anomaly will be circular and yellow in color as seen in the images. If it is streaking, then it could be convection or air loss from the window. Imagine the wildest, most crazy sUA application you can think of. Congratulations, you just looked into the future. One of the applications is evaluation of concrete bridge decks with an sUAS infrared camera. This image shows delamination of the bridge deck and possible moisture intrusion in the yellow areas or thermal anomalies in this iron bow pattern. In the 3 to 5 wavelength of the infrared spectrum, we find the midwave camera. The midwave camera is primarily used for inspection of leakages in oil and gas components. However, it may also be used in flat roof membranes. The image on your left shows a Vision aerial hexacopter with the FLIR GIS 320 camera. This image was taken with a midwave camera and identifies potential hydrocarbons leaking from a pump jack installation. This is identified by the cloud or the smoke effect coming from the base of the pump jack. It is important to note that today we have just touched base on some of the applications for sUAS thermography. Learning how to properly collect the data, interpret the imagery, and producing a professional deliverable requires training. Please check out our certified thermography training at infraredtraining.com. You can also download a free copy of FLIR Thermal Studio and FLIR Ignite at the websites below. I want to thank you for joining us today in the Level 1 Small Unmanned Aerial System Thermography Applications. This is just a small snippet of applications that can be performed from the air.